Now this what I call a two-state sorter is the best example of it is optical polarization. And the idea is, I'll just go ahead and put a couple of things up here. The idea is that it's mathematically the same as spin up and spin down. That's the other very simple quantum system that you learn about halfway through a quantum course, is the idea of the electron spin up, down,
Yeah.
right?
We just have two.
And you just have two possibilities. Yeah, which is an amazing thing, a magical thing, you might say, okay? And spin, the mechanics of the spin is something we're wrestling with. We're trying to figure out really what is that? What's going on there, you see? We have a much better picture for a two-state system if we look at light, look at the optics of polarization. Okay, those are the two states, X polarization and Y polarization. If we study that, we begin to feel we can understand what that's doing. So that's the one I'm going to pick on for the first part of this little story. As far as the physics goes, I'm going to pick on X and Y polarization as an example of the simplest quantum mechanics, the beginnings of the matrix formulation of quantum mechanics. And that's what's so good about the Feynman approach, is you don't get all tangled up with wave functions, which are infinite number of possibilities. You see, a continuum, a wave function in X has an amplitude for every point there, and if you were a continuum, you have an infinite number of points. So that's an infinite dimensional situation, you see. And Feynman says, no, let's start with 2. 1's already too simple, but 2, you can get all of the basic formalism and the basic ideas of both the quantum mechanics and the group theory that's behind it. So that's why I was a little surprised when I found that Feynman and Schrödinger had contempt for the mathematical descriptions of group theory, because they're the same thing. You see, quantum mechanics is group theory, as we're going to show. We're going to show that eventually. Okay? But here's the basic idea. You have, in general, some number of states. Could be approaching infinity, but we're going to keep that down to 2 or 3 or 4 for a long time before we get talking about the group theory of wave functions. So this is the basic idea, is that something that's coming along in a beam that can take on n different values gets analyzed by some sort of device, some sort of sorter. Somebody sorts the beam into state 1, state 2, state 3, and state n. And here we just have 2 possibilities for the spin a half, spin up, and spin down. Those are the only 2 possibilities. If you're talking about the, this is the Stern-Gerlach experiment, which is a very big surprise to everyone that was beginning to understand quantum mechanics. It was a big surprise. And it's also, if you look at the old experimental results, it's really amazing that they could make any conclusions from that at all. It's a very smeary result. It's sort of a blob here and a blob here, this kind of funny shape. And that's what we were seeing out here outside of the magnet. This is much clearer. This is much clearer. This is just a piece of calcite. This is perfect for Arkansas because you can pick calcite crystals. I don't know if there are any of them around. I was actually looking for some of them, or I've got a bunch of them here. But anyway, if you take a calcite crystal and put it down on a piece of paper, you see 2 images. one with a polarization this way and one with a polarization the perpendicular. So there's a professional splitter, but this is just a crystal of calcium carbonate. The light comes in with any polarization, so all polarizations, just plain old white light that's got every possible polarization, and it splits them, it sorts them into X and Y polarization. That's really amazing. But it's something that, well, I would say that the human race has known about this for how many thousands of years. Anywhere they had calcium carbonate, like Arkansas, these mountains here have, especially down near Ouachita, calcite is literally lying on the ground. I don't know if you've ever gone down, but that quartz and other crystals are there too, but you can get these things just for free by going hiking. Okay, so here's a quantum mechanical experiment that you can do outside, and it's very simple. All of our laser optics devices have prisms that separate. We're going to talk a little bit about that. I just want to give a sketch of what's going on to make a Brewster prism and sort the polarization. Because I want to emphasize that you're really understanding quantum mechanics requires a little bit of getting your head adjusted to waves interfering and doing various things. So that's what we're going to do here. So I want to show you just a basic idea of the geometry of sorting polarization states in Brewster's angle. And this is another thing that we ought to have on our website that will edify people about some basic optics. This is quantum optics. So the idea here is we've got a flat surface with a crystal of some kind, could be glass actually, it doesn't have to be anything, just something with a different index of refraction, and we're shining light down, and some of it reflects with the symmetry that you learned from your optics, right? The angle of incidence, okay, is equal to the, I've got it written backwards here, angle of reflection. These two angles have to be equal on a perfect reflection of some light of wavelength lambda 1. So that's, at first, all that's happening. But what happens also is, depending on how the speed of light is in these two medium, we'll have a speed c1, which will be, if this is a vacuum, 3 times 10 to the 8 meters per second, the speed of light. But then the speed of light in the glass may be, well, sometimes it could be faster, actually. Phase velocity can really be anything at once, but most of the time it's slower. I say a factor of 2 in leaded glass, right? This would be 2 times slower. This would be half the speed of light, and this would be full speed of light for the vacuum. Okay? So this is Snell's law. Do you remember Snell's rule for calculating what the angle theta 1, theta 2 is? This little thing here. That's important. Here's a blow-up of the triangles that sit here on this surface with a wavelength lambda 1 coming in, and then we're not going to be able to change the frequency, but we will have to change our wavelength in order to get a speed that is half as big as it was out there. So this little triangle right here has a wavelength lambda 2, whereas this triangle right here coming in has a wavelength lambda 1. Okay? So the idea is that lambda x here, that's this distance right here along the x-axis, okay, that times the sine of this angle, okay, this theta right here. You can look at this from the side. There's the base, there's the altitude. This is lambda x sine of theta. And then this thing right here, same idea, except now the theta's over here, is the wavelength lambda 2 equal to lambda x sine theta. That's the wavelength of these waves that are in this slow medium as compared to the fast vacuum. Does that make sense? Okay. So there's the index rule. That's what it's called. Index of refraction is the I've got it buried in this thing. This would be an index of refraction times the speed of light, where n was 1/2. Here, the index is 1. So that would actually be the speed of light if this was a vacuum. Okay, so far so good. Okay? Well, the fun thing is, what about the polarization? Here comes this light. It could be polarized this way, it could be polarized this way, this way, this way. It could be any angle. We're going to break them up so that the polarization consists of stuff that's out of the board. We'll call this the z-axis. And then stuff that has a definite angle, namely this angle theta 1 attached to it, we'll call this the y direction. So this will be a combination of the x direction and the y direction of polarization. So we're going to be looking at this thing and looking for a very interesting angle called Brewster's angle. And I'll explain that in a minute, but let's just look at where the polarization comes in. We're going to have a z polarization indicated like it is in most of your elementary textbooks. It's like an arrow pointing out of the screen, right? These little circles indicate z polarization. And then the arrows that are lying around in the plane, like those, because light has to be orthogonal to the k vector, the wave vector, so the light can have any polarization in a plane of the plane wave. Okay, and I hope you didn't get that wrong on your ENM.
We divide the polarization into two directions, z direction and xy direction.
Better way to say it would be you express it as a linear combination
of two
of those two directions, exactly. And making sure that you keep it perpendicular to the k vector, or parallel to the plane of phase.
Pointing vector.
And that pointing vector is probably a better name because that's where your momentum energy is, absolutely. So here comes this weird thing we call a light wave, and some of it's going to go down here and some of it's going to come out there, okay? And the question is, what is going to happen to it? Now, the way I like to remember this is these guys right here. You know, they're coming down, you know, these guys that are in the perpendicular direction, the z direction, okay? If it was just a pencil coming down here, and this was a nice smooth surface, then I can see very easily them just bouncing very nicely off of that surface, okay? Whereas when you come in like this, it's, you know, you can just imagine it's going to dig in, you see. So I would expect to see more of the light, you know, from that crazy argument, going down this way, okay? And more of this light going up this way. And that's really what happens. But at Brewster's angle, which is satisfying this equation, I'll come back to this in a minute, but at Brewster's angle, all of the light polarized this way goes this way. None of it, all of the light polarized this way, okay, gets pushed in, okay, gets sucked into the glass. And none of the light that's polarized that way comes out here. This can go either way. This one can, but that's the basic idea is that all of the light, if you pick this angle right, is going to have polarization this way. And none of it will have polarization this way. So we're going to sort the light. This will be the beam that takes the polarization that dug in. This will be the light that takes the polarization that did the nice bounce off the plane there. Okay, now I've got to explain what that means by showing just a little more complicated diagram. Okay? The idea is that this particular angle, which is close to Brewster's angle but not quite there, when this light that's polarized this way gets going and starts oscillating the charges here, okay, in this direction. So that's what the charges due to this polarization are going to do. The in-plane polarization as opposed to perpendicular, the XY polar combination polarization is going to be oscillating like this, and whenever any charge oscillates, it broadcasts light more or less perpendicular to the dipole moment. And this again is group theory at work. This is symmetry at work, which we're going to study later on in great detail. But right now, I just want to say is that the only component of this that makes it up there is this one. This is what's going up there right now. Very little polarization in the direction that is in the plane of this thing. As I said before, this stuff is having a good old time bouncing. A little bit of it goes down, but a lot comes out this way. Okay? And millions of dollars were made by Edwin Land because of this. Edwin Land is the fellow that invented polarized plastic. Okay, now unfortunately I only have one sheet. Looks like right here. Maybe I have some more here. But yes, here we go. Polarized sheet. This is a thing that's polarized this way. And I have here a piece of plastic, which if I turn it this way, you see it gets dark, right? So that's what sunglasses do. Sunglasses are put so that they block polarization this way. The stuff that echoes off very easily and for most angles, you're getting that, you know, and it's glaring you. So you put on Edwin Land's polarized glasses and it blocks this polarization, and suddenly the road turns dark in a certain angle, which is called Brewster's angle. It's actually very perfect in that direction. Okay? So this geometry shows that, and the idea is, and I'll just jump to the end here, the idea is you want to fix it so whatever light is going down this way is pumping along the angle of reflection. So here's the statement. Brewster's angle is where you make the theta 2 angle. That's this angle right here, the angle of the actual direction of the polarization of the wave in the plane. Okay? You make that angle equal to the complement of this phi1. Is you make it equal to this angle. That's the trick. Make theta 2, this angle, equal to this angle. Now in the preceding slide that wasn't true. Here theta 2 was a little bit less than pi over 2 minus theta 1. This is a little angle right here. That's a pretty big one right there. You can see that pretty clearly. They're close enough so that we get very small amounts of that polarization, but still, it's coming through. You're getting it in your eyes if you don't have the glasses on. Okay? So, that's what we're demanding. We're asking that this is that. Okay? Now, we have the index rules associated with lambda 1 over lambda 2 cancels the lambda x, so I get sine theta over sine theta 2 is equal to the ratio of the speeds of light. That would be the index of refraction in this case, or the inverse of it, depending on how you count. So this is giving us a very nice equation for Brewster's angle, because the sine of theta 2 now equal to this is the cosine. So I get a tangent of theta 1 is equal to the ratio here. Okay? So that's in a nutshell. It's a very, shall we say, hand-waving description of the optics of the waves that are polarized. But it's the simplest I could come. This is the most Feynman-like explanation I can give for Brewster's angle. But you've got to realize that what's really going on here is we have a charge here radiating up this way. All the charges in here are radiating in this direction. You see, they're they're oscillating in this direction, and that does not cause anything to happen in that direction. And that's what I want to mention. One thing by Feynman that makes this really clear that you'll have to read about to learn more about it. But this is called Feynman's lever. That's the basic idea. Whereas this guy, these guys, the ones that are doing this, they're very happy to radiate around the dipole radiation. So they're sending along a very strong signal with this polarization, and absolutely none of the polarization in that direction. And Feynman's lever is something that is described here. And this is from the other quantum mechanics book. Now, at this point we can stop before we actually describe Feynman's lever. I'm going to do that in just a minute, but I want to make sure you understand how you get at this stuff quickly. Okay? So I'm going to go ahead and try to do it on the screen. That's probably this. The other computer's in the shop, so it's not there. Let me just click on this thing, and up comes this textbook. Okay? And I happen to know that this is in unit or chapter, depending on how you read things, 6. Okay? This is the use of symmetry representation products of finite groups, is what that was. So this is a book that I finished in 1993, which is a long time ago. Okay? And so everything else that we've done has only been published on the web. Simply because it's too much to put on paper. Especially the way we're doing the lectures, which is every time I get a new thing, it's a new slide, just to put one more sentence, you see. So, we're going to fill a Babylonian library just from one course with paper, right? But you don't use paper, you use electronics, so the pages are basically free. That's the whole idea of this. But this is old-fashioned here. Now, I want to point out how you use this. This is a book which, if you don't have the actual paper version, these are the paper pages, okay? But you're going to be looking at separate PDF files for each chapter, like this one, okay? And so the PDF file starts right there, and we're looking at, let me go back quickly here to see what page this is located on. I will bring this guy up again. We're on page 517 of the book, okay? We got to find out what page on the PDF, right? And I'm jumping, I happen to know it's in the 6th chapter, it's a way to find that fairly easily. But let's, I'll go ahead here and look back at this, okay? So we got to look for page 517, okay? There's there's a little slide rule I made, okay? 510, 515, 16, 17. It looks like it's on page 76. Okay, that's the way you use the index. Kind of crazy. Well, someday we'll work out some way you don't have to go through this step, but we don't have that yet. So I just wanted to make sure that you saw that. So that means I have to, when I'm looking at this thing right here, I've got to go find page 76. Okay? Now, what I'm going to do here is I'm going to put this in the view mode. Full screen, I think, will work it. Is that right?
Mm-hmm. That's 22.
And maybe I have to do something else to get this. There should be a little thing. This one isn't doing it. I'm thinking, where does the page number show up on this? Presentation mode?
Try presentation mode.
Okay, let's go and view in presentation mode. Now that's another thing that probably is worthwhile. TC recommends Chrome, which is what I'm using. But the other browsers will do this too. It's just that sometimes they aren't as easy, and as I said, I forgot. So let's enter the presentation mode and see if I can find. I don't see them.
Hover in the corner over here, see what pops up. No, the other corner.
The other. Oh, here we go. Okay, there we go. So I can select the page number is what I was going to do. That just makes it bigger. Let's see. When I was doing this at home, I had a thing that let me show the page number.
There's 3 browsers we primarily use. They're all 3 different. You need to play with them to figure out which one you prefer.
Yeah, that's what
Safari,
I'm saying here.
Chrome, and Firefox are all 3 vetted. They all display things differently, so just dive right in and find out.
Let me see if I can. I mean, what you can always do is you can just crank through the thing.
See, there's showing
You just
page
grab
1.
this thing and go.
There's
like
showing
this.
it right next to the scroll bar.
Oh, it is showing. I was hoping for something that I could actually put the thing in, but let's just brute force our way up to page 70, 3, 4, 5, and 6. So there it is. Okay. Whoops. There we go. Feynman's letter. Okay. Now, what's Feynman's letter? This is, to me, this is amazing. This is in volume 2 of his books. But you also have. We need to put more references to that. Just the link to the free Feynman volume. It's free now. Just in the last couple of months, a new version that's been all cleaned up. There are a lot of errors in the original book, but it's free. Just as free as our stuff. So, be aware of that. This is in second volume, okay? And the idea is, and I used to have that little thing with the plus charge over there. There's a little mechanical version of this. Just imagine a ruler with a unit vector on the end, okay? Unit vector E sub R, okay? Good old-fashioned unit vector right there, okay? And you've got a charge, okay? And you're going to take that charge all over the place, okay? Whatever velocity, acceleration, it goes into this formula. This is where the charge is at an earlier time, t minus r over c. So you have to know what r is at the moment. And it's picking up the signal that's come out to it, okay? And we're trying to figure out what's the electric field at the origin, okay, due to you moving this charge, okay? Now normally in your electromagnetic Jackson and the rest of these books, Panofsky and Phillips, this is done by Leonard Vickert potentials. And it's a mess. This is closed form. This is just beautiful. All you have to know is where you are. That's the Coulomb term. Everybody knows that one, right? That's, if you stood still, this would be the answer. Okay? Unit vector with a minus sign on it if you're talking about a positive charge, okay, that is coming, the electric field would, for this charge, be negative the radius, pointing backwards, okay? And if you're moving, if you've got a velocity, you've got a current, okay? This is the induction term right here. You take the derivative of the unit vector. All you have to do is know the derivative of the unit vector. Okay, and this derivative could be a little complicated if you're changing the radius at the same time. But let's suppose you're just moving perpendicular. Then you wouldn't be. So you'd just be interested in the unit velocity times the speed. Okay? That would be the electric field if you didn't change the velocity. But if you do, that term is added. And that's the radiation term. End of story. You're done. This is it. It's exact. It's relativistically correct. And I think that's amazing. Now, the derivation of it is not simple, but it gives you one, and I've worked on others. I haven't got a simple way to get this, but boy, it is so powerful. And then here's your magnetic field. You just cross. So if you want to study a synchrotron or some weird laser, one of these free electron lasers, or stuff they're doing at SLAC, you want to do it? It's the formula to use. Okay. Now what it shows is, if I've got a charge here and you're there, and I go like this, you're not going to feel anything. I have to do this to make you feel something. You see? So you get a much better feeling for what's going to happen to somebody out there if you wiggle the charge. Now what we need to do is take this over and put it in the linearized theory of gravity, where they do vector potentials for gravity and all that stuff. Vector fields and vector potentials. That's the other thing. We don't worry. Where's the vector potential? You have to figure out where that is. It's the time derivative of this thing, right? But we could do gravity the same way. If I have a mass here, okay, that would be nice, right? Wouldn't you like to know what the tiny little gravitational field is due to me doing that? I mean, these are all things that just haven't sort of surfaced yet in our standard way of educating. This is a really good example of that, of Feynman doing something that is so better than what everybody else does, and nobody makes use of it. The books get written, and we don't go beyond.
Sorry. In this equation, when we move the charge perpendicular to
the radius vector.
The radius.
Yeah.
We don't have the third term because we don't see any change in that direction. Yeah.
Well, this is a derivative of both factors.
Yeah. No, the third term.
Yeah.
We don't see it is zero. The third term, because just the third
one.
The third one.
This is a vector. Yeah.
Yeah, in the third one we don't see anything.
That's what's cool about it.
Yeah.
And that's the one, see, that's the one
But
that you
we can see something in there.
Yeah.
We can see something in induction term.
Yeah. You do. That's right.
Because R will change.
Yeah. And of course you've got a double.
Yeah, yes, we have
there.
this.
Right. This one sort of works out to be more or less inversely with the radius. This is 0 power to the radius.
Yeah.
It's so cool. There's so many cool things about it. Yeah. And obviously, if you just slide, this doesn't move. It's only interested in that point and the distance. And if you keep distance the same, then you can factor those out of there. But yeah, it's really a beautiful thing. I think it deserves a lot more attention. Okay. Well, that's about all I have to say about the beginnings of the sorting process for polarization. We're going to do a lot more of that later on. But now I want to get down to the bookkeeping. This is the Brock-Het, Dirac-Brock-Het. Well, I would describe it as the accounting, the way you keep your quantum mechanical books in order most efficiently. And Dirac is the person that discovered this. It's since been adopted by the mathematicians. Let's go ahead here and show some of the notation. And what we really want to do is we want to be able to analyze what happens if I have this crystal and another one just like it. Or it doesn't cost you that much to get a professional version of a Brewster polarizer, and our lasers are full of them now. They're mass produced, so they're $100 or something for a really good one. It's not terribly expensive to get something that really works well. But the idea is that we're going to have, say, some initial state coming up from a laser beam, hitting this thing, and then it's going to split this polarization, which is some cockeyed angle, into what this one calls X and Y. So out of the other side of the crystal, and I'm exaggerating on the distance between the two beams, there's going to be a X polarized light and a Y polarized light. And if I'm going to call this one X, then I've got to use a prime symbol on this one's X. That is, the prime indicates its view of what an X-axis is. And perpendicular to that is this axis right here, where on the other beam this is coming out. And we're going to put a stop to that light. So this is a device that turns arbitrary polarization into some lesser amount of X prime polarized light. So that's a basic analyzer or sorter. It's a beam sorter. I use the word analyzer for something that's coming later. And this is following Feynman's terminology, more or less. So as this says, and by the way, this is located in this book. And let's take a quick look at that, where this is and where you can read the words that go with these figures right here. I'll go ahead and make this disappear, and then we'll come back to it. But we'll see these figures and some stuff that goes with it. So let me hit this one real quick. This is the textbook that I call Quantum Theory for the Computer Age, or the target of this is atomic, molecular, and optical physics. When you get to this thing, you got to click again. There you go. Okay, so here are all the units, and this stuff is in Unit 1. The relativity stuff, not as good a version as I'd like of relativity, but this was a start a few years ago, 10 years ago. we wrote this. Now we have much better, and I'll show you where that stuff is when we need it. But these are the units, each one with about 3 chapters of this quantum text. Let's go to the first one. That's a interfering two-state wave there, and there's more states being interfered there. That's what the title is. So this is the actual full title page. Here are the units showing their chapters, and we're just interested in, right today, chapter 1. Okay, and so that'll come up fairly quickly here. You ought to read the preface just to get an idea, you know, some of the stuff I've already told you about. This is a guide to the entire book here. I'm going to do a better job of that with figures in it later. But this is the unit that contains this description. That is, we're going to be counting photons, whatever they are. That's something this laboratory does really well. This is Professor Singh and Rita Vias's area, is counting, or what does it mean to count? The statistics of light is what they study. And do some really weird waves while they're doing it. So here's the chapter number 1, and there's the N particle thing that we talked about before. Here is the tube, just a sketch of a 2-electron spin, but here's the picture. Okay, unpolarized light splits into X and Y. Unpolarized light splits into X and Y. We throw away the Y. That's the killer here. And this goes through, and if it's an X-polarized analyzer, it's going to pass it, and there won't be anything that would come out here. None appears, as it says. So I just wanted you to see where this stuff was. There's the Brewster prism right there. This book does not have the graphics I showed you of the geometry. That's extra. But someday I'll put that in there too. There's the spin guy right there, the gyromagnetic ratio with a spin a half. Description of spin a half a little bit and all this stuff, where I indicate here that we really want to understand that too. But it turns out all of this stuff was spinor analysis, which came from Hamilton's quaternion algebra. This was 1843. All of that stuff got applied by George Stokes to polarization. So polarization really came first in the mathematical analysis. This is not appreciated by many people, except people that do what's called ellipsometry. That's the study of the polarization ellipse. We're going to do a good job of that later on. Okay? I think that's important because future spectroscopy is going to make big use of that. We're already counting the cosmic background as polarization. I wonder why that did that. Let me come back here and get us, there we go. Okay, well let's pause for a minute. If you have any questions about what we do, I'm going to go back now to the original lecture. Yes,
just a quick statement. For this class, we have a portal page that wasn't yet shown that has both textbooks broken out.
Yeah, it has them all
broken
basically.
Out, and
yeah.
So it'll be our main reference page. It should have been that one link that we had. Can you reference when you?
Why don't you go ahead and use this one, because as I said, the other computer's in the shop. And
all I need is that link that was in the email I sent you.
Well, let's go back to the lectures then, right here.
Okay.
Oh, do you actually want the link in the that's in the email?
Yeah. There is one that would be best. It'd be less fumbling.
Okay.
As long
Let's
as
go
you
ahead.
don't mind.
Let's go ahead and do that. Won't hurt.
But you'll see your.
What I'm going to do is I'm going to go back to the Finder here and bring up. This was not running, so let's get it running again. And then you can search. Go ahead and search for whatever it is you want to get. Oh, and it has to give you the mail, so that just click that thing out of there. Yeah. And there we got John Wick and Megan. It's a brief commercial here. And I'm pretty sure it's in the mailbox there.
See, this is what we didn't want up on the board.
You could actually do the first part of the email address and have it look for it as a content. That's one way to search, right? Oh, there's some stuff.
All right, here's the Learn It title page, and then software apps. This is your overall. This has more material than just this class.
Yes, I went to this.
Okay, this is your best
This
line
is your
launch.
This is a good starting
Yes.
point.
Okay.
And just go to
Classicals
group theory.
here. The group theory that we're working on, that one we were just looking at, right there.
I'll go ahead.
Just this.
And also, don't forget this one. This is just the book without the lecture notes. But that's the book without the electrons. It's 130 computer age right there.
Mhm.
This thing up here has more than that.
It's specifically designed for this course.
Yeah, there's the title
page.
page for this course.
And then you'll see there's 2 textbooks listed.
Yeah, this is the old one.
Textbooks.
This is the old one,
Yeah.
and that's the new one.
Yeah.
So there's
And we were looking at
one
the new
central
one.
launch.
Looking at the new one.
And then further down the bottom, you'll have lectures specific to this class. There's, you'll get to what we're covering today.
There it is, right there. Yeah, that's it.
And then other supplemental materials such as, well, if you want to reference other classes or related papers and talks.
Which we're going to be filling up.
Yeah, we'll be
Some
adding
more
to
stuff.
this as the class
Yeah.
goes on.
Yeah, it's a living thing, so you can expect some
Just
changes.
I have to go to the group theory, and after that I will be there.
You could keep this preceding page in your bookmarks, since
Yeah.
you already know it. And then
Yeah, you
can
keep
get
it on whatever computer you're using in the storage. In the thing, so that makes it easy to. You should mention that we also keep last year's, and right now they're parallel, but
Oh.
2013. But you'll see 215 filling up. There's the detailed lecture listing. There's 213.
click that, and then
So-
that brings you to the one he showed you earlier in the lecture.
Yeah. So that takes care of that.
Yeah, just wanted to point that out. That both texts, since he references both texts and the PDFs, they're all there right from this page, whichever way you want to go. It's available to you.
And the other thing that I find really terribly annoying, but is fun, is the fact that the colors of the spectrum, right, is going through this thing. If you don't like that, just click this, and they'll shut up. But you see, you can click it again. If you don't, that's the trouble. Yellow's hard to read on some computers, so all you do is click this thing and put some other color there and then stop it. Okay?
It's just frills.
Yeah, these are frills that, make it fun.
Sorry, did we start with the quantum theory in computer age or the principle of symmetry? We started with that.
That
we are
book,
at the chapter 1 of
well,
that text.
there's unit 1,
We are at the unit 1.
yes, and here's the detailed text listing right here, okay? There's unit 1, we're looking
Yeah.
at chapter 1, the analyzers,
Yeah.
okay?
Got it.
And now we're about to start stuff that's in chapter 2, transformation matrices. We have about 20 minutes or 30 minutes left of the class here. We're going to discuss a little bit of that.
Yes.
There's a clock there. There's a clock going backwards over there.
Yeah.
Yeah.
4 and 5.
So we'll be doing a little bit of this, and then we're going to do some nifty ways to look at eigensolutions. And that's an appendix with review. Okay, so all of the units that are finished have typically 3 chapters, maybe an appendix. This one is a little unusual in that it has 4, but most of them are just 3. So, it's a pretty well organized book. We'll change something, but not much, I think. Okay, does that make some sense? I mean, you said you were lost. I can believe it.
Yeah.
I get lost in it, as you can see. Okay, so we'll leave the browser and go back to our lecture here. And the point I want to make is that we already have a pretty good feeling for what the amplitudes are for, say, an X-polarized or an X-prime polarized light beam that's coming along here might do to a analyzer that's got its charge tracks oriented either to the x-axis or to the y-axis. That's the way I model a calcite crystal. It's pretty phony, but it's not totally phony in the sense that these are directions where it's easy to move and the charges will respond to the component in that direction. And then there's some little guys here that respond to the component that's in this direction. And it's the output from those two. One of them has a speed that makes it refract up to this way, and the other one has a phase velocity that makes it refract down to this way. So that's really what calcite is something that has different light speeds depending on your polarization. That's what's making the calcite work. Now that's something we need to have a better animation of some kind. I mean, we've got to put our thinking hats on to see how to build something like that. But that's really, this model is kind of what's going on in the solid to make this analyzer that splits the light beams up according to their polarization. The magic, of course, is that it splits them into perpendicular, always. It's always perpendicular. There's some symmetry going on there that makes that happen. So the basic idea is these big X charges here slide this way, but they can't be moved by a field this way, and they have a certain speed. And these Y charges that are on this rod right here sliding back and forth, that's all they can do is go this way, according to whatever component your field is, this much for them, that much for this one, you see. And it's those projections, sines and cosines, that make the transformation matrix, quantum transformation matrix that we're looking for. So I'm just summing up what it is we're doing here to make a transformation matrix. Now we're going into the bookkeeping. But that physically, that's roughly what is going on physically, the idea of a transformation matrix. So the point is that if we Y prime block it, Y prime polarized light block stop sign, none of it gets through to go through this crystal, okay? All we have is X prime, okay? And we let the X prime through, and we're going to take that to be XY analyzed. This is X, that's Y. This is X prime coming in, like that, at some angle theta. Okay, so that's the way I'm going to produce the transformation matrix, the group operator for polarization, if you will, group matrix. Okay, so here's the bookkeeping. This is the Feynman-Dirac, and it's really Feynman's interpretation of the Dirac matrix in this situation where we're talking about light waves. Semi-classical light waves, coherent state light waves, all kinds of fancy names go onto this that are hiding more details, but the basic geometry of it is exposed. So this is the amplitude of a state M, that's X, after state N prime, that's X prime, is forced to choose from available M types, X and Y in this case. That's all it can choose. Does that make sense? I should say, does it make more sense than what you would get in an ordinary quantum mechanics book where they talk about spin a half comes along here and it gets to choose spin up and down, you see? And then somebody's going to give you an amplitude for that. Here we can calculate it. Just from projection. Just from projection. This one right here. X prime to go to X is cosine theta. That's the ratio. Multiply that by whatever your amplitude was before, and you've got your output coming out here. Isn't that pretty simple? this was why, after I studied Feynman for a long time, I was really freaked out by the fact that he did not use this. What's really funny is the other guy, his competitor, the guy that, Schwinger, that worked on field theory too. There's a third guy, Tomonaga from Japan, but Feynman and Schwinger were kind of, Feynman was a young, brash kid. Schwinger was well-established physicist, for, you know, very formal, very powerful mathematically. You see, here's Feynman coming with this weird kind of mathematics, right, and claiming that he can understand stuff more easily than Schwinger could. Now, all three of them got Nobel Prize for doing this stuff, but this is very Feynman-like, this sort of thing. And I was very surprised that he didn't use it. But what's funny is Schwinger did, but only in later time of his life. When he was at UCLA as a senior, you know, what do you call it, an old professor, emeritus, right? Very senior guy giving lectures. He actually made little calcite things. And Rick Heller has this collection. Rick Heller at Harvard, a friend of mine, has a collection of these things that Schwinger made. Now, if Schwinger had only done that earlier, I mean, his mind was kind of opening up, so he's more like Feynman now. Not just a big formal guy, right? He's thinking the way Feynman did, you know, physically. You see, trying to get the students to understand polarization, okay? And that it's just science and cosines. So is spin, but that's getting ahead of the story. So is spin a half. Same mathematics, essentially. It's called the group SU2 if you throw away the overall phase. It's called U2, unitary group in two complex dimensions. That's what U2 stands for. And that's what we're working on here, as a subgroup of U2. Okay, this will all make sense later on. You're looking very puzzled, but that's really what's going on here. If you're doing quantum mechanics of the ordinary kind, which satisfies the orthogonality and completeness rules, which we are going to, quote unquote, Feynman derive, then you're dealing with a unitary group of two dimensions, which is a big and complex and very interesting group. Unitary transformations in two complex dimensions. We have to define what unitary means, you know, all that kind of stuff, but here's how we're going to do it. Okay? All right, let's look at a transformation matrix. I've got two things that can go here and two things that can go here, so I got four things that I'm going to display eventually in a what's called a transformation matrix. And that's going to be your first example of an operator that works on a beam of quantum objects to do something to them. Now let's see if there's anything I've left out. Let's go through this again. If we y prime blocked and let x prime through to be xy analyzed, the x output, that's this right here, the x output amplitude due to the x prime input, okay, and we're talking about this right here as the input, okay, is given by this notation. And you got to remember that Feynman and Schwinger were both Jewish. Hebrew, which is a Jewish main language, there's Yiddish too, but Hebrew is read from the right to the left. You start on the right and you go to the left. Now there are lots of other languages that do that too, I guess, or many of the Middle Eastern languages do that. Okay? So quantum mechanics does that. You always have the initial guy here and the final guy here. And you'll have a whole bunch of these things all lined up. That's the same thing, initial, final, then the new initial, new final, so. So you should be aware that we read that way, and I'm following that convention. It makes sense to do that now that it's been established. Okay? Now, what's the Y output? Okay? Well, that's that Y output right here, amplitude, due to X prime input, is Y X prime. And it's going to be a sine of theta. This one is a cosine, that's a sine. Okay? So we've got half of the transformation matrix now. You need the other half. If we X prime blocked, and let the Y prime through, okay, well, we get two more results. Okay? So that's what we're going to be letting through now. We're going to be letting through something that's going like this. And we want to see, how does it show up with these things responding their way to that? These guys right here respond and give us, right here, okay, a Y output. Okay? I've stopped that guy, I'm running that guy, okay? There's Y prime goes to X, okay? This is Y prime, it's got a component this way, it will come out of the X hole, right? So this is the X output amplitude due to Y prime input. And now you have to be careful. Sure, it's sine, but what's the sign of the sine? It's over here on the negative side, right? You got a phase factor. That's the tricky thing about this. You've got to keep track of the phase. And more than that, you've got to keep track of a complex number, because everything here is oscillating, right, at, say, 600 terahertz if it's a green light. So all of this stuff is wiggling. It's all resonance and interference of waves. So you got to keep track of whole complex numbers, not just plus and minus. As we get going here, we'll see what that amounts to. And then, okay, we block the X prime. Here comes Y prime. Y prime's going to go in and get sent in both at once, the X direction and the Y direction. Now we're asking, what's the Y direction going to come out to be? Okay. Well, now it's a cosine. But it's up, not down, so it's a plus cosine, not a minus like this one, which is on the negative side of the coordinate system X and Y. Well, here's the actual values for the angle that we've picked. We picked a 30-degree angle. So we're getting an amplitude of a half out of the sine wave. Let's see if that's right here. Sine of 30 degrees is a half. I believe this angle is actually should be a little bit bigger than that, but anyway. But the cosine, that's the big one, is 0.866, square root of 3 over 2, it turns out. Okay? That makes sense? Whoops.
It's back. It's back.
There's that loose connection. Yeah. The gods of anti-quantum mechanics. All right. So, there's our transformation matrix. These are all of the components being described. So this is an introduction to the bracket transformation matrix. The hyphen here is put there intentionally because what we want to do is extract from this matrix the bras and the kets as vectors that are called state vectors. That's coming. But I just wanted you to see that all of this stuff is based on, and there's so much in physics that, modern physics, that is like this. This is the heart of the bookkeeping, is a matrix or a collection of vectors is really what it is. But it's a collection of two kinds of vectors, and that's what's really screwy here. What I want to show you is the abstraction of the Bra and the Ket vectors from the transformation matrix. It's a very simple idea, but it's very profound at the same time. And then we'll end with just a little discussion of scalar on matrix products. But you see, by setting this thing up in such a nice way, like Feynman and of course Schwinger at the same time. So what I want to do is I want to discuss the Ket, and then later on we'll take on the Bras. So here's the transformation matrix that we were given, or we found. And we had to be careful that there was a minus sign for that one. Okay, that's when y prime came in and asked to knock on the door of the x. And it was hanging over in the negative section, so we got a minus there. All the others were positive, either sign, and there were two on the diagonal or cosine. Now you've played with this matrix for other things. This is a rotation matrix. Okay? We're just redoing the theory of rotating x and y into x prime and y prime. But it's representing a physical process that's doing essentially that. We're analyzing by rotating. Okay? So what I want to do is talk about how you get a Ket state vector from a transformation matrix. You just pull it out. See this thing right here? If I cover up the x and the y, this is our state x prime that was on its way out of the first analyzer when I blocked this one. I blocked that one. I kept this one. Okay? So just bring it down and write it right here. Bring the numbers that go with it, cosine and sine. That is a Ket that represents a state. If you want to think of this as classical in some way, out of this thing, after the blockage, comes my x prime. It's getting ready to go into an x, y analyzer, but that's our input right there, x prime. That's our input state. It's written like a Ket because it came first. And here are the numbers that go with it. Now this is what we call abstract reasoning, right? But we are literally, it should be called extract. We're extracting the vector, right? I don't know. I don't want to get too fancy with the syntax, but you see that there's some truth to this. There's some truth that makes sense here. And then I pull the second column out. That's my y prime state. Now this one does have a minus sign, as we pointed out. Okay? So that's abstracting these state vectors from a transformation matrix. Okay? Just the Ket part. Okay? Here's a picture again of where they stand relative to each other. X and Y are lined up with respect to the screen. This other guy is turned up here at 30 degrees. 30 plus 30 is 60. I would make an equilateral triangle if I finished it by reflection. Okay? So, theta equal plus 30 degrees. We don't actually need that other projector today, but we'll stick with this one. The idea is that the rotated Kets, these are x prime and y prime, or if you use the old Gibbs notation, just writing a vector as a thick x and y, right? Like Gibbs notation in calculus books. And you might even put a little arrow over the top of it, right? Well, the arrow's already built in here, you see. There it is, pointing, right? Now you have to realize that Dirac, who invented that notation, that Dirac notation, okay, we're saying that this vector x prime here is a linear combination of x and y. There's the x and there's the y, right? And there are the linear combinations right there. Okay, so it's cosine of theta times the x plus sine of theta times the y. It's pretty obvious, okay? But Gibbs would write it this way. Now, I'm going to tell a story about how Dirac dealt with this that shows you that even the very most brilliant put their pants on one leg at a time. In any case, here's the other one, okay, up here. Let's see if I've got this y prime guy. Got it written here somewhere. Yeah, we're taking this guy right here, the minus sine theta cosine theta. Okay, so there's the y prime being written as a combination, and the first component here is the one that has to do with the x direction. It's got a minus sine theta, and the second component's got a cosine. That's the y prime part of this matrix. Okay, so this just lays it out as clearly as I can think of to do it, more clearly even I think than Feynman did, because he was using some three-dimensional vectors and he didn't have at his access a very good draftsman, or he didn't feel like drawing. He had a very good talent with drawing. So here are the four components: cosine theta, sine theta, minus sine theta, and cosine theta of the transformation matrix. You see, that's their geometrical picture. Okay, now Gibbs would say, why are you wasting your time with 2 extra lines? I just draw this thing with 1 symbol. You've got 3 symbols. There's a point. He has a point, okay? Gibbs vector notation, I would write it like this. There's my cosine theta, the dot product of x and x prime. I'm talking about vector x and vector x prime. Okay? There's the y, has a dot product like that. Okay, and then there's y prime, same thing. There's a minus sine theta that we have right here. We got a big fat x. It's 1 symbol. I have to write it extra fat, right? Or else put an arrow, which is 2 symbols. But this is 3 symbols, right? So you might say, what are you doing this for? You're making shorthand into longhand, right? Well, let's go to the other side here, the bra. That's where Gibbs is left behind. Okay? We abstract the rows of this transformation matrix to make them. And they point this way. Because they're going to be acted on eventually by operators of various types of optical machinery, and they're going to be operated on from the right. These guys here are going to be operated from the left. Okay? So the flat side of these vectors tells you where you can put an operator. So we do the same trick. We just go through the same stuff. And you need to do this because all of the components that are possible, the worst thing we've had is a minus sign on one of them, but we're going to have complex numbers in all 4 of these positions. All 4 of those positions can be complex, and will be. And we have to use complex numbers simply because complex numbers have a really nice way to deal with oscillation. These things are sitting there oscillating, and they're like clocks. And there's a phase space that we're going to be defining where the real axis is here The imaginary axis represents the velocity. The real axis represents the where is it, the position. This is the velocity direction. And if you're positive velocity, you're going this way, so you're going to be going clockwise. So the oscillators that we're talking about, and this is taking us from quantum mechanics to relativity, but the idea of having clocks sitting there in space and time is very much a part of making clarity out of quantum mechanics and relativity, which is our modern physics. So all of this is needed because we have to have a state that is conjugate to this one being conjugate to that one, or vice versa. Conjugate means time reversed, basically. In any case, let me tell you what Dirac did. He wrote his entire quantum mechanics book. The first one, it's a very famous book. It's what considered still worth reading, although it's not like Feynman. It's not chatty. It's not pleasant reading. And it doesn't have very many figures or pictures. He was, very much an algebraist, very much a thinker, just like Schwinger. Schwinger was very algebraic. Feynman more graphic. Okay, the difference between parts of the brain that get developed, or that you tend to develop, you see. So Dirac went entirely through writing a major quantum mechanics book that he thought was going to set for once and for all how people would do it. And for vectors that he envisioned later to be the kets, he called alpha. And he used a fat alpha, just like Gibbs did. And for vectors that were the other side, these, he called beta. The bras were betas, the others were alphas. The whole book went through. Now I know this because Jan Smit, who is a famous magnetic, shall we say, phenomenologist, but he's a really excellent theorist, a very good teacher at University of Southern California, one of the years I spent there. Jan Smit had a copy of Dirac's book. I mean a copy that he had copied by hand out of the Leiden University Library while Nazis were on all sides of this, what was called the Free University, where the Germans agreed not to go and yank you and take you and put you on the front lines. I mean, it was a horrible time. So he's in there. He couldn't take the book out, but he could copy it. He did. He copied alpha, beta, beta, alpha, 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 beta, 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 alpha, alpha, beta. And then after the war, Dirac said, "Why don't I just do this?" And that's how Dirac notation came to be. It took a long time before he realized, I'm tired of writing alphas and betas all the time. I want to make something that's logically more clear. And so far, this is the best notation we have for this. And you can see a little bit better here, but we still haven't really got to it. We're going to notice that we can re-abstract this thing, you see, and cover up the things that are on the left here, and that's called a unit operator. But we'll get to that. That's what's called a completeness relation, you see. So all of this stuff will, make a little bit more sense later on. A couple of more things. We're just at the end here. Unit vector kets, and that's what Gibbs would call them, but he would put a little hat over it probably, are represented in their own, in this case x and y is our starting basis here, by 1, 0, 0, 1. That means xx is always 1, yx is 0. We got to make axioms out of that. That's what Feynman makes starts to make the 4 axioms for quantum mechanics, which map onto the 4 axioms of group theory. That's why I say group theory is very much this. So this last part here, the scalar products and the components are the same. They're called direction cosines. Even though this is a sine, it's a direction sine, but it's a direction cosine when you take the angle that goes with it. here's the dot product, you see. So we're talking about a scalar product of bras with kets. Gibbs wouldn't make the distinction. There's no difference between this vector and this vector. You see, you've got to make that distinction when you're talking about something that's going to be complex, something that's going to oscillate, something that's going to be doing interference, all sorts of crazy wave things. So we're going to be talking about the state that's in the X base, a general state psi of a polarization, which will be the polarization vector of the moment. But we use the psi notation because that's become so much prevalent in our lore of quantum mechanics that we can write a ket this way, and we can write a bra of that way as well. There's this duality that goes with this thing. But you see, what we're doing here is taking that number, and it's just the, in this case it would be sine of whatever this angle is. And then it would have an amplitude. This thing was a unit. This might be bigger than unit. In quantum mechanics where you could have something bigger than 1. Our first quantum mechanics will be unitary, so it will always be less than or equal to 1. So you can look at these components just the way we looked at the transformation matrix. These are the components of the state written in the prime basis. These are the components here written in the original XY basis. So those are making connections with the idea of the scalar product, which is very elementary. So these are two different viewpoints of the same thing. Whatever this state is, this is just another way of looking at it. Another reference frame, if you like, you see. And there's a relativity of these things, too, you see, just like there's a space and time. It all comes together very nicely if you play your cards right, with bras and kets. Okay, so there's transformation matrix relating these. This shows you that you can write the components in the old XY basis in terms of the components in the new basis. And here's an ugly Gibbs-Dirac notation here where I put psi sub x, psi sub y. What I really mean is psi left-hand sub of x, psi left-hand sub y of x. Okay? I call this ugly because it's a mixture of Dirac and the old-fashioned component notation, but still, it's valid. Okay? And the proof is that you can do this is just to look at that each x is an expansion. So that implies that I could stick that x, which is this expansion right here that we worked out before, in and immediately get, using the same coefficients, a combination of x prime and y prime that gives me the original components in x and y. And the last little piece here is to do it for y as well. Okay? So that shows that matrix works. Okay? And here's the inverse. Now, this is stuff we'll do in more detail later, but I think you see the logic. Trying to make the physics, which is polarization amplitudes, into a geometry and an algebra that carries us through everything we're doing right now in the current state of quantum mechanics. The bookkeeping is really quite amazing. Okay, I'm going to stop right there. We're